There is a question that has lived quietly in the minds of scientists, philosophers, and dreamers ever since humanity first looked up at the night sky and wondered whether anyone was looking back. It is not a question born of fiction or fantasy. It is a question rooted in hard physics, in cold mathematics, and in the strange, beautiful, terrifying reality of a universe so vast that the human brain is physically incapable of truly comprehending its scale. The question is this: what happens when a civilization sends its most precious message into the darkness, not knowing whether anyone will ever receive it, not knowing whether the silence on the other end is temporary or eternal, and not knowing whether the very object carrying that message will survive the unimaginable journey across the void? What happens when an entire species decides to speak into the cosmic dark, and the cosmic dark simply does not answer? This is not a hypothetical. This already happened. And right now, as you are sitting wherever you are sitting, reading these words or hearing this voice, there is a small golden disc attached to a spacecraft that was built before most people alive today were born, drifting silently through interstellar space at roughly 17 kilometers every single second. It carries within its grooves the sounds of rain falling on a forest, the song of a humpback whale, the first movement of Beethoven's Fifth Symphony, a child laughing, a mother speaking to her newborn baby, and the brainwave recording of a woman who was, at the moment of recording, falling in love. It carries greetings in 55 human languages, including languages that were already ancient when the Roman Empire was young. It carries a map that is supposed to tell any finder where it came from, and it is, by every honest calculation that science can produce, almost certainly never going to be found. Almost certainly. Those two words carry tremendous weight. They are the words that science demands when we are dealing with probabilities that are so crushingly small that calling them impossible would be slightly inaccurate, but calling them possible would feel almost dishonest. The golden record may never be found, not because it is lost in any conventional sense, not because someone made a mistake, but because the universe is so incomprehensibly large, and space is so incomprehensibly empty, and the distances between stars are so incomprehensibly vast, that the act of sending a small golden disc into it and hoping it will be found is in the language of mathematics. Something between the bravest gesture and the most beautifully futile act that any civilization has ever performed. Before we get into all of that, I need to ask you something. Right now, pause for a moment and think about the farthest place you have ever been from your home. Maybe it was another city, another country, another continent. Now think about the distance from Earth to the Moon, which is roughly 384,000 kilometers. That distance is already beyond most people's experience. Now think about the distance from Earth to the Sun, which is about 150 million kilometers. That is 400 times farther than the Moon. Now think about the distance to the nearest star beyond our Sun, Proxima Centauri, which is about 40 trillion kilometers away, or roughly 4.2 light years. That is approximately 266,000 times farther than the distance from Earth to the Sun. And now, hold that number in your mind and understand that Voyager 1, after 48 years of constant travel, covering roughly 17 kilometers every second without stopping, has covered a distance of just over 25 billion kilometers, which means it has covered, after nearly half a century, approximately 1/1600th of the distance to the nearest star. Think about that. Nearly 50 years of travel at unimaginable speed, and it has barely begun the journey. If this is making you feel small, then you are beginning to understand what this video is really about. Because this is not just a story about a spacecraft, this is a story about distance and time on scales that human cognition was never designed to process. This is a story about what happens when a young, hopeful, curious species tries to reach across those distances with the best of what it has and what it is. And this is a story about why the mathematics of the cosmos may mean that reach was always destined to fall short. But before we get there, we need to go back to the beginning, because the beginning of this story is one of the most remarkable things that happened in the 20th century, and most people have never heard the full version of it. The year was 1977. The Cold War was at a particularly tense phase. The United States and the Soviet Union were locked in a competition that extended into every domain, including space. NASA had been to the moon, had launched Skylab, had sent Pioneer probes to the outer solar system. But the Voyager missions represented something genuinely different. They were born from a rare and fleeting opportunity that the solar system itself had arranged. Every 176 years, the outer planets of our solar system align in a configuration that allows a single spacecraft to visit all of them, one after another, using the gravitational field of each planet to slingshot itself to the next. This alignment, which scientists and mission planners called the Grand Tour, was occurring in the late 1970s and would not occur again until the mid-22nd century. If NASA did not launch in 1977, no human then alive would live to see the next opportunity. 2 spacecraft were prepared. Voyager 2 was launched first, on August 20th, 1977, followed by Voyager 1 on September 5th, 1977. Despite their numbers, Voyager 1 was the faster of the two and would overtake Voyager 2 within months. Each was a remarkable engineering achievement, weighing approximately 825 kilograms, powered by radioisotope thermoelectric generators that used the natural radioactive decay of plutonium-238 to generate electricity. Each carried 11 scientific instruments, and each carried something that no spacecraft had ever carried before, something that had nothing to do with scientific measurement and everything to do with what kind of species we are when we are at our most ambitious and our most honest. The idea of including a message to potential extraterrestrial civilizations on the Voyager spacecraft did not come from a committee or a bureaucrat. It came from Carl Sagan, who was at that time a professor of astronomy and space sciences at Cornell University, a prolific science communicator, and a man whose fundamental philosophy was that the universe was not a cold and indifferent place, but a place filled with possibility and mystery, and perhaps with others who were asking the same questions we were asking. Sagan had already been involved in the Pioneer plaques, the small gold anodized aluminum plates attached to Pioneer 10 and Pioneer 11, which had been launched in 1972 and 1973, and were the first human objects intentionally designed to carry a message beyond the solar system. Those plaques showed a man and a woman, a diagram of the hydrogen atom, a map using pulsars, and the spacecraft itself. They were remarkable, but they were simple. Sagan wanted more. For the Voyager missions, Sagan assembled a committee. The members included Frank Drake, the astronomer who had devised the famous Drake equation for estimating the number of communicating civilizations in the galaxy, and who had conducted the first modern SETI search in 1960. They included Timothy Ferris, a science writer and the record's producer. They included John Lomberg, an artist who had helped design and visualize the project. They included Linda Salzman Sagan, Carl Sagan's wife at the time, who had helped with the Pioneer plaques. And they included a young creative director named Anne Druyan, whose involvement in this project would lead to one of the most moving and unusual love stories in the history of science, a story that ended up literally encoded on the disk itself. The task they set themselves was staggering. They had to decide what to put on a physical object that might, conceivably, be encountered by a non-human intelligence at some point in the remote future. They were not writing a scientific paper. They were not crafting a diplomatic message. They were trying to represent an entire civilization, an entire planet, an entire species, in a way that would be comprehensible to something that had never had any contact with Earth and had no reason to share our assumptions, our perceptions, our aesthetic sensibilities, or our conceptual frameworks. They were, in the most literal possible sense, trying to speak a universal language, and they had no guarantee that such a language existed. What they produced was a 12-inch copper disc, plated first with nickel and then with gold. The gold plating was not decorative. Gold was chosen because it does not corrode. It does not react with the sparse molecules of the interstellar medium. It is chemically stable over timeframes that dwarf the entire history of human civilization. The disk was housed in an aluminum protective cover, and onto that cover was electroplated a sample of uranium-238, a detail that sounds alarming until you understand why it was included. Uranium-238 has a half-life of 4.468 billion years, which means it decays at a precisely known and measurable rate. Any civilization that found the record could use mass spectrometry to measure how much of the uranium had decayed into its daughter products, and from that measurement, they could calculate exactly how long the record had been drifting in space. The record was its own timestamp, accurate to within a fraction of the age of the solar system. This was not an afterthought. This was the kind of thinking that happens when a team of extraordinary people are working at the very edge of their creativity and their knowledge simultaneously. The cover of the record also contained detailed instructions for how to play it and how to decode the information encoded on it. In the upper left corner was a drawing of the phonograph record with a stylus positioned at the beginning of the first track, with binary notation indicating the correct rotation speed. One rotation takes 3.6 seconds, expressed in units of 0.7 billionths of a second, which is the time period associated with a fundamental transition of the hydrogen atom, an interval so basic to physics that any civilization capable of building technology capable of reading the record would almost certainly understand it. The cover showed how to construct pictures from the encoded signals, explaining that each image was made of 512 vertical lines, similar to an analog television signal, and that the first encoded image, a simple circle, was provided so that any finder could verify they were decoding the image geometry correctly. In the lower left corner was the pulsar map, an updated version of the one used on the Pioneer plaques, showing the position of our solar system relative to 14 known pulsars, with the precise period of each pulsar encoded in binary. And in the lower right corner was a diagram of the hydrogen atom in its two lowest energy states, establishing the fundamental unit of time used throughout the entire encoding scheme. Inside the disk itself, the committee had encoded 116 images, though one of these was a calibration image used to help any finder verify their decoding process. The images begin with the most universal language available, mathematics. The first real image is a circle, establishing that the finder is correctly interpreting the geometry of the encoding. Then comes the definition of the mathematical constant pi, then definitions of physical quantities, then a diagram of the solar system with the relative sizes of the planets, then images of the Earth from space, the Moon, diagrams of dinar structure and the chemical composition of our atmosphere, and then gradually, carefully, the visual record expands to show life itself. There are images of dolphins, birds, insects, trees, landscapes, deserts, forests, and mountains. There are images of human beings from many different cultures, a mother nursing her child, children at play, a family portrait, people eating, people working. There is a photograph of a supermarket, which some committee members debated fiercely, arguing that it presented a distorted and materialistic picture of humanity, and others defended as an honest depiction of how food is distributed in a modern society. There is a photograph of the Arecibo radio telescope in Puerto Rico, the largest single-dish telescope in the world at the time, included as evidence of our technological capabilities. There is a page from Isaac Newton's Principia Mathematica. There is a photograph of Egypt and the Red Sea and the Nile River taken from orbit. Every image is an attempt to communicate something real about what we are, where we live, and what our world looks like. But the images, as remarkable as they are, may not be the most moving part of the record. That distinction belongs to the sounds. The committee assembled a remarkable audio portrait of Earth and its life and its people. There are natural sounds: the wind, rain, surf crashing on a beach, thunder, the sound of a fire burning, the sound of mud pots bubbling in a volcanic field, the sound of a stream, and the sound of animals, birds calling, frogs, hyenas, elephants, chimpanzees, and humpback whales, whose complex, haunting, multi-octave songs were included from Roger Payne's landmark 1970 recording album, Songs of the Humpback Whale. There are human sounds, footsteps, heartbeats, laughter, the sound of a kiss, the first words a mother speaks to her newborn baby, and the sound of a person thinking, in the most literal possible sense. That last item requires its own explanation, which we will get to shortly, because it is perhaps the most extraordinary thing on the entire disc. There are greetings in 55 languages, ranging from modern English, Mandarin, Hindi, Spanish, Russian, and French, to ancient and extinct languages including ancient Akkadian, which was spoken in Mesopotamia roughly 4,000 years ago, ancient Greek, Latin, Hittite, and Sumerian. Carl Sagan's 6-year-old son Nick recorded a greeting in English. The United Nations Secretary-General Kurt Waldheim contributed a spoken statement. There is a message encoded in Morse code, the Latin phrase per aspera ad astra, which translates as through hardship to the stars. And there is a printed message from President Jimmy Carter which reads, "This is a present from a small, distant world, a token of our sounds, our science, our images, our music, our thoughts, and our feelings. We are attempting to survive our time so we may live into yours." And then there is the music. The music selection for the Voyager Golden Record is one of the most carefully curated and emotionally resonant playlists ever assembled, not just for any spacecraft, but arguably in the history of recorded sound. The committee worked for months on music selection, and the final list includes 27 musical pieces representing cultures from every inhabited continent. From Western classical tradition, there is the first movement of Bach's Brandenburg Concerto No. 2, performed by the Munich Bach Orchestra under Karl Richter, a piece of such mathematical precision and emotional warmth that it is often described as one of the most perfect compositions in the Western canon. There is Bach's Gavotte in Rondo from the Partita No. 3 in E major, performed by violinist Arthur Grumio. There is Bach's Well-Tempered Clavier, Book 2, Prelude and Fugue No. 1 in C, played by Glenn Gould. The committee clearly believed, and it is difficult to argue with them, that Johann Sebastian Bach was the most universal of Western composers, that his music combined mathematical structure with profound emotional depth in a way that transcended cultural context. There is Mozart's Queen of the Night aria from the Magic Flute, performed by soprano Edda Moser, a piece of such extraordinary technical and emotional virtuosity that it remains astonishing even after hundreds of years. There is the first movement of Beethoven's Fifth Symphony in C minor, performed by the Philharmonia Orchestra under Otto Klemperer, 8 minutes and 49 seconds of what may be the most instantly recognizable sequence of notes in all of human music history. That thunderous opening motif of 3 short notes and 1 long da-da-da-dum, which Beethoven himself reportedly described as fate knocking at the door. There is Beethoven's String Quartet No. 13 in B-flat, Opus 130, Cavatina, performed by the Budapest String Quartet, and Carl Sagan would later describe this piece as among the most profound and moving things he had ever heard. A piece that he believed communicated something about the depth and loneliness of human feeling that no words could match. There is Chuck Berry's Johnny B. Good, whose inclusion was controversial in certain quarters, with some members of the wider community dismissing rock and roll as adolescent music, to which Carl Sagan responded with characteristic wit. There are a lot of adolescents on the planet. There is Louis Armstrong's Melancholy Blues, which carries within its 3 minutes something of the whole history of American music. There is Blind Willie Johnson's Dark Was the Night, Cold Was the Ground, a wordless slide guitar piece recorded in 1927 that Sagan described as the loneliest sound he had ever heard. A piece so suffused with ache and beauty and yearning that it seems like the musical equivalent of looking at the night sky and feeling the full weight of human smallness and human longing simultaneously. There is Court Gamelan music from Java, recorded at the Pura Pakualaman Palace. There are Peruvian panpipes and drums. There is a Navajo night chant recorded by ethnomusicologist Willard Rhodes. There is music from Senegal, from the Mbuti of the Ituri rainforest in what was then Zaire, from the Solomon Islands, from the Aboriginal Australians, from Azerbaijan. There is a Bulgarian folk song, Izlel Ye Delio Haydatin, sung by Valya Balkanska, whose voice, clear and ancient and heartbreaking, has been drifting through interstellar space since 1977. There is shakuhachi flute from Japan, performed by Goro Yamaguchi. There is Indian classical music, a raga called Jat Kahan Ho, sung by Sushri Kasabai Kirkar, a vocalist of such extraordinary reputation that she was reportedly known in India as Queen of Music. There is a 7-minute piece of Chinese Guqin music, Flowing Streams, performed by Guan Pinghu, and there is Stravinsky's Rite of Spring, the Sacrificial Dance, conducted by the composer himself, a piece of music that caused a riot at its premiere in 1913 and that now floats peacefully through the darkness between stars. There was also a piece of music that almost made it onto the record but did not, the Beatles' Here Comes the Sun, from the Abbey Road album. Carl Sagan and his committee wanted it desperately. The Beatles themselves were apparently agreeable to the idea, but EMI, the record label that held the copyright, demanded $50,000 per record for 2 records, while the entire Voyager Golden Record had been produced for only $18,000. So, Here Comes the Sun, one of the most beloved and optimistic songs in the history of popular music, a song about warmth returning after a long cold winter, never made it to interstellar space. Whether this fact says more about the cosmic missed opportunity or about the music industry is a question each person must answer for themselves. Now, about those brainwaves. This is the detail that takes the Golden Record from a remarkable scientific and cultural artifact to something that feels genuinely, almost unbearably, human. Anne Druyan was the creative director of the Golden Record project. She was 27 years old, and she was brilliant and passionate, and deeply committed to the idea that the record should represent not just the products of human civilization, but the experience of being human. The subjective, interior, feeling reality of what it is like to exist as a conscious creature on this particular planet. She proposed that the record should include an electroencephalographic recording of human brainwaves, the actual electrical activity of a human brain thinking and feeling in real time. The committee agreed, and Anne Druyan volunteered to be the subject. She was connected to equipment that recorded her neural activity, her pulse, her eye movements. For approximately an hour, she meditated and directed her thoughts through a series of topics and experiences. She thought about the history of Earth. She thought about the evolution of life from single-celled organisms through 500 million years of increasing complexity to the moment she was sitting in that recording studio. She thought about the accumulated knowledge of human civilization, about mathematics and physics and music and art and literature. She thought about the problems that humanity faced, the threats of war and environmental destruction, the persistent failures of our better instincts. She thought about what it felt like to be a human being in 1977, aware of history and afraid of the future and hoping, desperately, for something better. And then there is what she thought about at the end of the recording, which she has spoken about in interviews many times since. On June 1, 1977, just days before the brainwave recording session, Anne Druyan and Carl Sagan had spoken on the phone and had, in the course of that phone call, realized that they were in love with each other. They decided to marry, and during the brainwave recording, with the electrodes attached to her head and the equipment recording every flicker of her neural activity, Anne Druyan was thinking about that. She was thinking about the experience of falling in love, what it feels like in the body and the mind and the chest, when you realize that your life has been permanently changed by another person. Those thoughts, that neurological record of a human being newly and overwhelmingly in love, are encoded on the Voyager Golden Record. They have been drifting through interstellar space since September 5, 1977. Carl Sagan and Anne Druyan married in 1981. They remained together, deeply connected, collaborating on books and films and television series, until Carl Sagan died of pneumonia in December 1996, at the age of 62. Anne Druyan has said in interviews that she finds a kind of comfort in knowing that those brainwaves are out there somewhere, moving through the darkness, carrying within them the electrical record of a moment of profound human happiness. She has also said that she finds it devastating that Carl never knew whether the record would be found. He spent much of his career hoping for contact with another civilization. He died never having received any sign that anyone else was out there. The record continues its journey without him. Before we get to the mathematics of why this record may never be found, I want to pause here and ask you to do something. If you have not already subscribed to this channel, please take a moment to do that right now. And if what you have heard so far has moved you, or intrigued you, or made you feel something about the nature of time and distance and human longing, please leave a comment below telling me what you would have put on the Golden Record if you had been on that committee. Would you have made different choices? Would you have included different music, different images, different messages? What would you want to send to the stars to represent everything you know and love about being alive? I read every comment. I want to know what you think. And hit the like button, because it helps this kind of deep, slow, meditative science storytelling reach more people who might need to hear it. Now let us talk about why the record may never be found, and let us start not with Voyager, but with a number. The number is 100,000. That is the approximate width of the Milky Way galaxy in light years. A light year is the distance that light, moving at 299,792 kilometers per second. The fastest speed that anything in the universe can travel, covers in 1 year. 1 light year is approximately 9.46 trillion kilometers. 100,000 light years is therefore approximately 946 quadrillion kilometers. That is 946, followed by 15 zeros. Write it out. 946 trillion kilometers. This is the galaxy that Voyager 1 is drifting through at 17 kilometers per second. At that speed, crossing the full width of the Milky Way would take approximately 1.7 billion years. To put that in context, 1.7 billion years ago, the most complex life on Earth was single-celled organisms. The dinosaurs would not exist for another 1.1 billion years after that. Human beings would not exist for another 1.699 billion years after that. The entire history of multicellular life on Earth would not fit into the time it would take Voyager to cross our own galaxy. And yet, the Milky Way is just one galaxy. There are an estimated 2 trillion galaxies in the observable universe. The distances between galaxies make the distances between stars look like the distances between cities. The nearest large galaxy to our own, the Andromeda Galaxy, is approximately 2.5 million light-years away. The observable universe is approximately 93 billion light-years in diameter. Voyager, at its current speed, would take approximately 1.8 trillion years to cross the observable universe. The universe itself is only 13.8 billion years old. Voyager would need approximately 130 times the current age of the universe just to cross the distance we can see. These are not numbers that have any intuitive meaning. The human brain evolved to navigate distances of tens or hundreds of kilometers, to track prey and predators, to find shelter and water. It was not designed to process numbers of this magnitude. But science does not care what the human brain was designed for. These are the actual numbers, and they are the foundation of why the Golden Record faces a challenge that goes far beyond any engineering failure or design flaw. Now let us look at where Voyager actually is, and what its actual journey looks like in these terms. As of 2026, Voyager 1 is approximately 25 billion kilometers from the Sun, or about 169 astronomical units. An astronomical unit is the distance from the Earth to the Sun, so Voyager is 169 times farther from the Sun than we are. It crossed the heliopause, the boundary of the Sun's heliosphere where the solar wind gives way to the interstellar medium, in August 2012, making it the first human-made object to enter interstellar space. Voyager 2 followed in November 2018. Both spacecraft are now technically in the space between stars, the vast, cold, thin ocean of gas and dust and cosmic rays that fills the volume between stellar systems. But here is the twist, the detail that most popular accounts of Voyager miss entirely. Being in interstellar space is not the same as being anywhere close to another star. Voyager 1 has been in interstellar space for roughly 14 years at the time of this writing, and it is still only about 1/600th of the way to Proxima Centauri, the nearest star. The heliopause is merely the outer edge of our Sun's direct influence. The gravitational sphere of influence of our Sun, the region where the Sun's gravity dominates over the gravitational pull of other stars, extends roughly to the outer edge of the Oort cloud, a vast spherical shell of icy bodies that surrounds our solar system at distances of up to 100,000 astronomical units, or about 1.6 light-years from the Sun. Voyager will not fully exit the gravitational influence of our Sun for approximately 30,000 years. In November 2026, Voyager 1 is expected to reach a milestone. It will become the first human-made object to travel one full light day from Earth. One light day is the distance that light covers in 24 hours, approximately 25.9 billion kilometers. This is being celebrated as a remarkable achievement, and it is. It is also, in the context of interstellar distances, approximately the equivalent of taking one step out of your front door on a journey that will take you to the edge of the observable universe. The nearest star encounter on Voyager's current trajectory is with a red dwarf star called Gliese 445, located in the constellation Camelopardalis. Voyager 1 will make its closest approach to this star in approximately 40,000 years. At that point, it will be approximately 1.6 light-years away from the star. 1.6 light-years is approximately 15 trillion kilometers. This is what astronomers call a close encounter. It is not close in any sense that a human being would recognize. It is the equivalent of a message in a bottle drifting across the Pacific Ocean and passing within 150 kilometers of an inhabited island without getting close enough for anyone on the island to see it, assuming the people on the island were not looking. Voyager 2, on a different trajectory, will make its closest approach to a star called Ross 248 in approximately 40,000 years at a distance of about 1.7 light-years. Neither spacecraft is heading toward any inhabited planet that we know of. Neither is heading toward any star system that we have any reason to believe harbors intelligent life. They are simply drifting, following the trajectories that the physics of their launches and their planetary flybys determined, into the void. Let us now confront the mathematics of detection directly, because this is where the story becomes genuinely deeply sobering. Voyager 1 is approximately 700 millimeters across at its widest point, the dish of its high-gain antenna. 700 millimeters. Less than a meter. In a galaxy that is 100,000 light-years across. For any civilization to find the Golden Record, one of two things would have to happen. Either that civilization would have to be conducting an extraordinarily thorough survey of interstellar space and happen to detect Voyager directly, which would require technology so far beyond ours that the comparison is difficult to make. Or Voyager would have to drift close enough to an inhabited star system that the civilization there would be able to detect it through some method, either visually, by radar, or by some other means we have not yet conceived of. The probability of either of these things happening in any time frame meaningful to human civilization, or even in any time frame meaningful to the existence of our species, is vanishingly small. To illustrate this, imagine you are blindfolded, and you are standing in the middle of the Sahara Desert, and someone has hidden a single grain of sand somewhere in the desert, and your task is to find it. Not with any tools, not with any assistance, just by wandering. That analogy is not quite right, because it actually overstates the probability by many orders of magnitude. The Sahara Desert has an area of approximately 9 million square kilometers, The volume of interstellar space in the Milky Way is approximately tens of cubic light-years per star. The disparity in scale between the grain of sand and the desert is nothing compared to the disparity between Voyager and the galaxy. And yet, there is a layer to this story that makes it even more complex, and that layer involves not just the question of whether Voyager will be in the right place, but whether there will be anyone in any place who might find it. This brings us to one of the most profound and unresolved questions in all of science, the question of whether intelligent life exists elsewhere in the universe, and if so, where it is and why it has not made itself known to us. In 1961, at a meeting in Greenbank, West Virginia, the astronomer Frank Drake, who was on the Golden Record Committee 16 years later, proposed a mathematical framework for estimating the number of technologically advanced, communicating civilizations in the Milky Way. The Drake equation, as it came to be known, is written as n equals r multiplied by fp multiplied by ne, multiplied by flel, multiplied by phi, multiplied by fc multiplied by l, where n is the number of currently active communicating civilizations in the galaxy, r is the average rate of star formation in the galaxy per year, fp is the fraction of those stars with planetary systems, ne is the number of planets per system with conditions suitable for life, fli is the fraction of those planets on which life actually develops, phi is the fraction of life-bearing planets on which intelligent life develops, fc is the fraction of those intelligent civilizations that develop technology capable of communicating across interstellar distances, and L is the average length of time such a civilization continues to transmit detectable signals. The Drake equation is not really a calculation in the traditional sense. It is a framework for organizing our ignorance. The first two variables, R and Fp, can now be estimated with reasonable confidence. We know from decades of observation that the Milky Way forms new stars at a rate of roughly 1 to 3 per year. And we know from the extraordinarily productive Kepler Space Telescope mission and subsequent exoplanet surveys that the majority of stars have planetary systems, with estimates suggesting that virtually every star in the galaxy has at least one planet. And that roughly 1 in 5 Sun-like stars has a planet in the habitable zone, the range of orbital distances where liquid water can exist on a planetary surface. Based on these numbers alone, there could be tens of billions of potentially habitable planets in the Milky Way. But then we hit the variables where our knowledge becomes thin and then disappears entirely. Fl, the fraction of habitable planets on which life develops, is unknown. We know of exactly one planet on which life exists, Earth. We do not know whether the emergence of life on Earth was a common outcome of planetary chemistry or a spectacularly rare accident. We do not know whether the conditions that led to life on Earth are easily replicable, or whether they required a particular and unusual combination of factors that might occur only rarely. We know that life on Earth appeared relatively quickly after the planet formed and became stable, within roughly 500 million years, which has led some scientists to argue that the origin of life is relatively likely given suitable conditions. Others argue that the apparently rapid emergence of life on Earth is simply a survivor's bias, that we are here to observe it precisely because it happened, and we cannot draw statistical conclusions from a sample size of 1. Phi, the fraction of life-bearing planets on which intelligent life develops, is equally uncertain. Life on Earth persisted for approximately 3.5 billion years in the form of single-celled organisms before the Cambrian explosion of multicellular life roughly 540 million years ago. Human-level intelligence emerged only in the last few million years at most, and civilization in the last 10,000 years. Intelligence may be a common endpoint of evolutionary pressure, or it may be a wildly improbable accident, a particular solution to the problem of survival that happened to work on Earth, but that might not emerge under different conditions. But the variable that most directly affects the probability of the golden record being found is L, the average longevity of a technological civilization. A civilization can only find the golden record if it exists, if it has developed technology capable of interstellar travel, or at least of detecting an interstellar object, and if it remains technologically active. If civilizations tend to destroy themselves shortly after developing advanced technology through war, environmental collapse, pandemic, or some other failure mode, then L could be very short, perhaps only a few centuries or a few thousand years. In a galaxy 100,000 light-years across, a civilization with a lifespan of a few thousand years is like a firefly flashing briefly in the darkness of a large forest. The probability that another firefly in a different part of the forest flashes at exactly the same moment, and that the two flashes overlap in time and space, drops dramatically as the lifespan of each flash decreases. Carl Sagan believed that L was the most important and the most uncertain variable in the Drake equation. He argued that the key question for humanity was not whether intelligent life existed elsewhere, but whether intelligent civilizations could survive themselves, whether they could navigate the transition from primitive technology to advanced technology without destroying their world in the process. He believed that the existence of the Golden Record was, in a sense, a statement about our own aspirations in that regard. The act of sending it was an act of hope. Hope that we would survive long enough to one day meet the civilization that found it. Hope that both our civilization and theirs would have managed to persist through whatever dangers attend technological intelligence. The fact that 60-plus years of systematic searching by the SETI Institute and other organizations have yielded no confirmed signal from another civilization is, in the language of physics, a data point. It is known as the Fermi paradox, named after the physicist Enrico Fermi, who reportedly asked at a lunch table in 1950, "Where is everybody?" If intelligent life is common in the Milky Way, and if even a small fraction of civilizations develop the capacity for interstellar travel or interstellar communication, then on the scales of time involved, any civilization that achieved this even 1,000,000 years before us should have colonized or at least contacted every star system in the galaxy by now. The galaxy is old enough that this has had ample time to happen, and yet we see no evidence of it. No megastructures, no signals in the electromagnetic spectrum, no artifacts, no visitors, nothing. The great silence. There are several scientifically serious explanations for this silence, and none of them are reassuring for the Golden Record's prospects. The rare earth hypothesis, developed by geologist Peter Ward and astronomer Joe Browley in their 2000 book of the same name, argues that complex life, meaning multicellular, differentiated, and eventually intelligent life, requires a very specific combination of conditions that may be genuinely rare in the universe. These conditions include a star of the right type, neither too hot nor too cool, neither too variable nor too active in terms of radiation output. They include a planet in the habitable zone with a stable, nearly circular orbit. They include plate tectonics, which drive the geological cycles that regulate atmospheric carbon dioxide and keep the climate stable over geological timescales. They include a large moon. Our moon stabilizes Earth's axial tilt, preventing the kind of dramatic polar wandering that would make the climate wildly unstable. They include a large outer planet, Jupiter, that acts as a gravitational shield, absorbing or deflecting many of the asteroids and comets that would otherwise rain down on the inner solar system with catastrophic frequency. They include a galactic location away from the dangerous central bulge of the Milky Way, where stellar density and radiation are too high for complex life to thrive. Each of these factors reduces the probability of complex life. The argument is that when you multiply all these probabilities together, the result may be that complex, intelligent life is extremely rare, perhaps unique to Earth. If the rare Earth hypothesis is correct, the Golden Record may be drifting through a galaxy that is, in terms of technological civilizations capable of finding it, essentially empty. Then there is the concept of the Great Filter, proposed by economist Robin Hanson in 1998. The Great Filter is the idea that somewhere in the sequence from simple chemistry to interstellar civilization, there is a step that almost no civilization successfully navigates. A filter that eliminates the vast majority of would-be spacefaring species. The terrifying question, which Hansen explored in detail, is where in that sequence the filter lies. If the filter is behind us, if the hard step was the origin of life, or the transition to eukaryotic cells, or the development of multicellular organisms. Then, we are the rare ones who made it through, and the silence of the universe is explained by the near impossibility of reaching our level. This is the optimistic interpretation. But if the filter is ahead of us, if there is a step between our current civilization and true interstellar capability that civilizations reliably fail to navigate, perhaps because they destroy their technological infrastructure before they can develop interstellar travel, then the silence of the universe is a warning rather than a reassurance. It would mean that the civilizations that could find the Golden Record have not existed long enough to find it. SETI researchers have noted that the absence of detectable signals is particularly telling, given that we have now been searching the electromagnetic spectrum for artificial signals since 1960. We have surveyed large portions of the sky at multiple frequencies with increasing sensitivity. We have found no signals that have been confirmed as artificial in origin. The most famous candidate, the WOW signal detected at the Big Ear Radio Telescope in Ohio in 1977, the same year Voyager was launched, was a narrowband radio signal of approximately 72 seconds in duration that bore the characteristics expected of an extraterrestrial origin. It was detected once and never again despite extensive follow-up searches. It was never explained, and it was never confirmed as artificial. The universe has maintained its silence. There is another dimension to the problem of detection that is specific to the physical nature of the Golden Record, and that is the question of its physical survival. The engineers who built the record designed it with extraordinary care for longevity. The choice of gold plating, the choice of copper as the substrate, the choice of aluminum for the cover. All of these were made with an eye toward the long-term stability of the object. And in purely chemical terms, under ideal conditions, the record could survive for an extraordinarily long time. Gold does not corrode. Copper, protected by the gold plating, does not degrade. The grooves encoding the audio and image data are physical structures, microscopic ridges and valleys pressed into the metal surface, not magnetic recordings or digital files that require active maintenance. If the record were kept in a perfectly stable environment with no radiation, no impacts, and no temperature fluctuations, there is a plausible argument that it could remain physically intact for 1 billion years or more. But interstellar space is not a perfectly stable environment. It is cold, with temperatures approaching 3 degrees above absolute zero, but the problem is not so much the temperature itself as the radiation environment. Interstellar space is permeated by cosmic rays, high-energy particles that travel at significant fractions of the speed of light and that carry enough energy to penetrate metal. Over millions of years, the cumulative bombardment of cosmic rays will degrade the surface of the record, eroding the fine grooves that encode the information. The damage will be slow, but it will be real. Scientists have debated exactly how long the record would remain readable under these conditions, and estimates vary widely depending on assumptions about the intensity of the cosmic ray environment and the exact mechanism of degradation. Some estimates suggest that the most delicate features of the record, the finest grooves encoding the highest frequencies of the audio signals, could be significantly degraded within a few million years. Others are more optimistic. But even the most optimistic estimates acknowledge that the record cannot survive indefinitely. Then there is the question of micrometeorite impacts. The interstellar medium is not entirely empty. It contains dust particles and microscopic debris, and while the density of this material is extraordinarily low, it is not zero. Voyager has been traveling through this medium for years, and at 17 kilometers per second, even a microscopic impact carries significant kinetic energy. The cumulative effect of micrometeorite impacts over millions of years is difficult to calculate precisely, but it is not zero, and it represents another mechanism by which the record could be physically damaged before it is found. And then there is the spacecraft itself. The Golden Record is attached to the exterior of Voyager, and if Voyager is catastrophically damaged or destroyed by some cosmic event, the record goes with it. A direct impact with a sufficiently large object would destroy both. the gravitational dynamics of the galaxy over millions of years could alter Voyager's trajectory in ways that become increasingly unpredictable over long timescales. In the short term, on the scale of tens of thousands of years, Voyager's trajectory is well understood. In the longer term, on the scale of millions or billions of years, the cumulative effect of gravitational perturbations from stars and molecular clouds makes precise prediction impossible. Voyager could, over geological timescales, end up following a trajectory that takes it far from any star system, or it could, by an extraordinary coincidence, end up passing through a system where a civilization exists and is capable of detecting it. This brings us to perhaps the most profound and specific problem with the Golden Record's pulsar map, the navigation key that was supposed to tell any finder where the record came from. The pulsar map is genuinely brilliant in concept. Pulsars are rotating neutron stars that emit beams of electromagnetic radiation, and because these beams sweep past Earth like the beam of a lighthouse, we detect them as regular pulses of radio waves. Different pulsars pulse at different rates, ranging from a few pulses per second to hundreds of pulses per second for the fastest millisecond pulsars. The periods are extraordinarily precise, stable to better than 1 part in 100 billion for the most regular pulsars, which is why pulsars are sometimes used as natural clocks. By encoding the positions of 14 pulsars in the sky relative to our Sun, and by encoding the precise period of each pulsar, the Golden Record's cover provides a kind of three-dimensional map that should, in principle, allow a finder to triangulate the position of our solar system in the galaxy. But there is a problem. Pulsars slow down over time. Their rotation periods increase measurably as they lose rotational energy through the emission of electromagnetic radiation and gravitational waves. The rate of this slowdown is different for each pulsar, and it is measurable and well documented for the pulsars we observe. For a civilization finding the record in 40,000 years, the change in pulsar periods would be detectable but manageable. They would need to account for the known spin-down rates of the pulsars, calculate the period each pulsar would have had when the record was created, and use those corrected periods to work out the timing of the record's origin and the position from which it was launched. This is hard but doable for a civilization with the physics knowledge to find the record in the first place. But for a civilization finding the record in 1 million years, the problem is significantly worse. For a civilization finding it in 10 million years, it is much worse still. Pulsars do not last forever. Over millions of years, pulsars slow their rotation enough that their electromagnetic beams weaken and eventually disappear, a process called pulsar death. Over long enough timescales, some or all of the 14 pulsars on the Golden Record's map may no longer be detectable. Their positions will still be in the sky, but without the characteristic pulsing signal, identifying them as the specific pulsars indicated on the map becomes much more difficult. For a civilization finding the record in tens or hundreds of millions of years, the pulsar map may be of limited utility as a precise navigation tool, though the positions of the dead pulsars could potentially be identified through other means if the finder had sufficiently detailed knowledge of stellar evolution and galactic dynamics. Ethan Siegel, an astrophysicist who has written extensively about this issue, has called the pulsar map hopelessly wrong in an article for Forbes, pointing out that even now, in 2026, the map is less accurate than it was in 1977 because pulsars have continued to slow down in the decades since it was created, and the precise periods encoded on the cover are no longer accurate for current observations. Any civilization attempting to use the map today without correcting for decades of pulsar spin-down would get a slightly wrong answer for the position of our solar system. The deeper point is not that the map is useless, but that it becomes harder to use the longer Voyager drifts before being found. The Smithsonian Air and Space Museum conducted an interesting exercise in 2017, the 40th anniversary of the Voyager launch, in which they recalculated the pulsar map using modern data on pulsar periods and spin-down rates. They found that the map's effectiveness as a navigation tool depends critically on how much time has passed since the map was created, and on the astronomical knowledge available to the finder. With the right knowledge, the map can still be used, but it is not a simple decoder ring. It requires significant astronomical sophistication. And then there is a deeper question about decodability that goes beyond the technical challenge of the pulsar map. The Golden Record assumes that any civilization capable of finding it will have developed senses and cognitive frameworks that bear enough resemblance to ours to make our communications comprehensible. We assume that vision is a sense that will be present, because the record contains both images and instructions for reconstructing images. We assume that the concept of a mathematical diagram is comprehensible, because the cover is covered in diagrams. We assume that the hydrogen atom is a recognized and understood entity, because it is used as the fundamental unit of time and scale throughout the encoding scheme. These assumptions are scientifically grounded. The hydrogen atom is the most common element in the universe. Mathematics, as far as we know, is universal. Physics is physics regardless of who is doing the observing. But the assumption that an alien civilization would interpret images the way we do is less certain. The process of looking at a two-dimensional representation of a three-dimensional object and understanding it as a representation of a three-dimensional object is something we do so automatically that we forget it is learned. Human children have to learn to interpret photographs and drawings. They do it quickly, because they have visual systems and cognitive frameworks that evolved specifically to process three-dimensional visual information and that naturally extend to two-dimensional representations. But an alien species with radically different sensory apparatus, perhaps one that navigates primarily by sonar like a bat, or by chemoreception like many insects, or by some sense we have not imagined because it does not exist on Earth, might have a very different relationship to visual representation. The image of a human figure might not be recognizable as such to a being that perceives the world in a fundamentally different way. Frank Drake and Carl Sagan tested the decodability of their record by giving it to scientists and engineers at Cornell University without any instructions and asking them to decode it. It took them effort, real effort, and they got some things wrong on the first try. These were human scientists with human visual systems in the same cultural tradition as the people who made the record, who knew the record existed and knew they were trying to decode it. The achievement of successfully decoding a message sent without prior warning by an utterly alien intelligence would be orders of magnitude more difficult. This does not mean it is impossible. Carl Sagan believed that the laws of physics and mathematics provided a sufficient common foundation for communication between any two technological civilizations. But it does mean that decoding the Golden Record would be a major intellectual undertaking even for a civilization much more advanced than our own. Now let us pull back and look at all of these factors together, because each one individually makes the Golden Record's discovery unlikely, and together they paint a picture that is, in the most honest and scientifically grounded terms, one of extreme improbability. The record is less than a meter across in a galaxy that is 100,000 light-years wide. It is travelling at 17 kilometers per second, a speed that is fast enough to be remarkable on human scales, but that makes the crossing of interstellar distances a matter of hundreds of thousands or millions of years. The nearest star encounter is still 40,000 years away, and even then, Voyager will not actually pass through that star system, but merely drift within a wide margin of it. The physical record will suffer cumulative radiation damage and potential micrometeorite impacts over the vast timescales involved. The pulsar map will become increasingly difficult to use as pulsars continue to slow and eventually fade. The civilizations that could find it may not exist, or may not exist for long enough to develop the technology needed to detect a small spacecraft drifting in the interstellar void. And yet, there is something important that needs to be said about all of this, because the mathematics of improbability do not tell the full story of what the Golden Record is and what it means. Before we get to that, let us briefly consider the other attempts humanity has made to reach across the void. Because the Golden Record was not our first attempt, and it was not our last, and seeing it in the context of these other efforts illuminates something important about what we are as a species. The first physical messages sent into interstellar space were the Pioneer plaques, attached to Pioneer 10 and Pioneer 11. Pioneer 10 was launched in March 1972 and became the first spacecraft to travel through the asteroid belt and make a flyby of Jupiter. After completing its scientific mission, it continued outward and is currently heading in the general direction of the star Aldebaran. Some 68 light-years away, at its current speed, it will not come close to any star for millions of years. Pioneer 11 was launched in April 1973, flew past Jupiter and Saturn, and is heading in the direction of the constellation Aquila. Both spacecraft carry plaques designed by Carl Sagan and Frank Drake, with artwork by Linda Salzman Sagan, depicting a naked man and woman, with the man's right hand raised in greeting, a pulsar map, a hydrogen atom, and a diagram of the solar system showing the spacecraft's origin. The plaques are simpler and less information-rich than the Golden Record, but they established the principle of physical cosmic messaging. In 1974, the Arecibo radio telescope in Puerto Rico was used to transmit a powerful radio signal toward the globular star cluster M13, located approximately 25,000 light-years from Earth. The signal, known as the Arecibo message, consisted of 1,679 binary digits arranged in a specific way that, when rendered as a two-dimensional grid, produced an image encoding information about the human form, Na, the solar system, and the Arecibo telescope itself. The number 1,679 was chosen because it is the product of two prime numbers, 23 and 73. A mathematical property that was supposed to make it obvious to any recipient that the grid had those particular dimensions. The message was transmitted on November 16, 1974, as part of a ceremony marking the upgrade of the Arecibo telescope. Any reply from M13, travelling at the speed of light, would not reach Earth for approximately 50,000 years. No reply has been received, but this was not expected in any time frame relevant to the people who sent it. The Arecibo message was, like the Golden Record, more of a demonstration of capability and a gesture of hope than a practical communication strategy. Since then, several other messages have been transmitted from Earth. In 1999 and 2003, a project called Cosmic Call transmitted radio messages from a telescope in Ukraine toward a selection of nearby stars. In 2001, a project called Teenage Message transmitted a radio signal from a Russian telescope. In 2008, a message called A Message from Earth was transmitted from the Evpatoria telescope toward the planet Gliese 581c, a planet in the habitable zone of its star approximately 20 light-years away. None of these have received responses, but the relevant distances mean that replies would take decades at minimum. The New Horizons spacecraft, launched in 2006 and famous for its flyby of Pluto in 2015, is now heading into the outer solar system, but it does not carry a Golden Record or any equivalent message to extraterrestrial civilizations. The Golden Record remains unique. No other physical object sent into space by humanity carries anything close to its richness of information and its emotional depth. It is the most detailed and the most human message we have ever sent into the cosmos. Now let us talk about what the Golden Record reveals about us as a species, because this is perhaps the most profound dimension of the entire story, and it is the dimension that matters most, regardless of whether the record is ever found. The committee that made the Golden Record faced a question that no group of people had ever seriously faced before. If you had to represent the entire human species, all of its knowledge, all of its art, all of its diversity, all of its history, all of its feeling, in a single object that had to be comprehensible to an intelligence with no prior knowledge of humanity, what would you put in it? This is not just a logistical challenge, it is a philosophical challenge of the deepest kind, because it forces you to ask what you actually believe is most essential about being human. What is the irreducible core? What, if you had to choose, is the thing about human civilization that you most want to survive, most want to communicate, most want to be remembered? The committee made choices that were not without controversy. The decision about what music to include sparked fierce debates. The The initial suggestion for the music committee was to include primarily Western classical music, on the grounds that Bach and Beethoven represented the highest achievements of the Western musical tradition and would best demonstrate the intellectual and aesthetic sophistication of our civilization. But others on the committee pushed back strongly. Alan Lomax, the great ethnomusicologist who had spent decades recording folk and indigenous music from around the world, argued that Western classical music represented only a fraction of human musical achievement, and that the record would be dishonest if it did not represent the full range of human musical expression. His argument won, and the final selection reflects a genuine effort at global representation, drawing from the music traditions of India, China, Japan, Azerbaijan, Senegal, Zaire, Australia, Peru, Mexico, Bulgaria, Georgia, the Solomon Islands, and Native American traditions, as well as the Western classical canon and American jazz and rock and roll. But even with these efforts, the record reflects the perspectives and values of its creators, who were predominantly American and Western, and who were working under severe time constraints, assembling the entire project in roughly a year. Certain decisions that seem puzzling in retrospect were made under pressure. The decision to include a photograph of a supermarket was debated fiercely, with some committee members arguing that it sent the wrong message about human priorities, that showing a building full of packaged food was not the most dignified or universally comprehensible image of our civilization. Others argued that it was honest, that food distribution is a fundamental aspect of how we organize society, and that showing it was better than pretending it did not exist. The supermarket photograph made the final cut. The decision about whether to show the human body was complicated by politics. The pioneer plaques had depicted nude human figures and had received angry letters from some members of the public who found the images offensive, complaining that NASA was sending pornography into space. For the Golden Record, NASA was reluctant to allow photographs of nude human beings. The committee compromised by including a silhouette of a man and a woman rather than a detailed photograph, and by including within the encoded images a more detailed anatomical diagram showing external human anatomy, positioned in a context that was clearly scientific rather than prurient. Carl Sagan later expressed frustration at this compromise, feeling that the prudishness of the decision was itself a kind of dishonesty about the human body. The selection of images made no attempt to show the dark side of human civilization. There are no images of war, of poverty, of famine, of environmental destruction, of violence. The humanity depicted on the Golden Record is peaceful, diverse, creative, and intellectually engaged. This was a conscious choice. Carl Sagan argued that the Golden Record should be an expression of our best selves, an aspiration rather than a confession. He believed that showing the worst of humanity to potential extraterrestrial observers would be neither accurate nor helpful, that the violence and injustice of our history were not the most representative or the most important things about us. Others have argued that this decision made the record a kind of idealized portrait rather than an honest one, that any civilization advanced enough to find the record and evaluate it would understand that we were showing them a curated selection rather than the full picture. These debates are never resolved, because there is no right answer. The question of what represents humanity is one that humanity itself has never agreed on. Different cultures, different individuals, different traditions have radically different answers. What the Golden Record represents, ultimately, is not humanity as a whole, but humanity as seen by a small group of thoughtful, passionate, deeply committed people who had 1 year to do the impossible and who did the best they could with the time and the knowledge and the resources they had. That is a very human kind of achievement. Let us think now about what has happened to Voyager since its launch, because the physical story of the spacecraft is as remarkable in its way as the story of the Golden Record that rides upon it. Voyager 1 was launched on September 5, 1977, from Cape Canaveral, Florida, on a Titan E rocket with an additional Centaur upper stage. It passed the Moon within hours and was headed toward Jupiter within weeks. It reached Jupiter in March 1979, performing a close flyby and returning the most detailed images of Jupiter and its moons ever taken to that point, including stunning photographs of the volcanic moon Io, which was found to have active volcanoes, making it the first body other than Earth known to have ongoing volcanic activity. Voyager 1 then used Jupiter's gravity to slingshot itself towards Saturn, arriving at Saturn in November 1980, where it made close approaches to several moons and returned extraordinary images of the rings in detail never seen before. After its Saturn flyby, Voyager 1 was directed on a trajectory above the plane of the solar system, which ruled out further planetary encounters, but positioned it to eventually escape the solar system. Voyager 2 followed a different trajectory, going to Jupiter in July 1979, Saturn in August 1981, Uranus in January 1986, and Neptune in August 1989. Voyager 2 remains the only spacecraft to have visited Uranus and Neptune, and its flyby of Neptune's large moon Triton revealed a spectacularly strange, geologically active world with geysers of nitrogen gas erupting from its pink nitrogen ice surface. After Neptune, Voyager 2 also headed outward into interstellar space on a different trajectory from Voyager 1. Both spacecraft were powered by 3 radioisotope thermoelectric generators, or RTGs, each containing about 4.5 kilograms of plutonium-238 dioxide. RTGs generate electricity through the natural radioactive decay of the plutonium, which produces heat, and that heat is converted to electricity through thermocouples. The system is elegant in its simplicity, requiring no moving parts and producing power continuously for decades. At launch, each spacecraft's RTGs produced approximately 470 watts of electrical power. But plutonium-238 decays with a half-life of roughly 88 years, which means the power output decreases at roughly 0.78% per year. By 2026, after nearly 50 years of operation, each spacecraft's RTGs are producing only a fraction of their original power output, probably somewhere in the range of 250 to 270 watts or less. NASA has been managing this power decline through a series of instrument shutdowns, turning off science instruments one by one as the available power decreases. In April 2026, NASA shut off another instrument aboard Voyager 1, specifically to conserve power and extend the spacecraft's operational life. The expectation is that Voyager 1 will lose the ability to operate any science instruments sometime in the next few years, and that engineering data transmission will continue for somewhat longer. After that, Voyager 1 will become silent, a dead spacecraft carrying a golden record, drifting through interstellar space with no way for us to know where it is or what it has encountered. It will cease to be a scientific instrument and become purely an artifact, a relic of a particular moment in human history, still moving, still drifting outward, but beyond our awareness. This transition from a living communicating probe to a silent artifact is one of the most poignant things about the entire story. For nearly 50 years, Voyager has been sending back data, a continuous stream of information about the solar system and then about interstellar space, about magnetic fields and cosmic rays, and the density of the interstellar medium and the nature of the boundary between the heliosphere and the void beyond. Its signal, which takes more than 22 hours to travel from Voyager to Earth at the speed of light, is extraordinarily faint, requiring the enormous antenna dishes of NASA's Deep Space Network to detect it. Even now, the transmitter on Voyager 1 outputs only about 22 watts of radio power, about the equivalent of a refrigerator light bulb, and by the time that signal has traveled 25 billion kilometers to Earth, it has spread out to a level so faint that detecting it is one of the greatest engineering achievements in the history of telecommunications. When Voyager finally goes silent, that connection will be severed. We will no longer know where it is in real time. We will be able to calculate its position from its last known trajectory and its known velocity, corrected for the gravitational influences it has passed. But we will not be able to confirm those calculations through direct communication. The spacecraft will be gone from our awareness in any practical sense, even as it continues its eternal drift outward. From that moment, the Golden Record will truly be alone. Now we arrive at the question that all of this has been building toward. Given everything we have discussed, given the scales of distance and time, given the uncertainty about the existence of intelligent life, given the physical challenges facing the record, given the mathematical improbability of detection, given the decoding challenges, what does it mean that we sent it anyway? What does it mean that a small committee of thoughtful, passionate human beings spent a year of their lives choosing the music and the images and the sounds that would represent everything human life has ever created and achieved and felt, and then sent that selection into the darkness without any reasonable expectation that it would ever be received? I think there are several answers to this question, and I think all of them are true simultaneously. The first answer is that the Golden Record was never primarily about communicating with alien civilizations. It was about communicating with ourselves. The exercise of deciding what to put on the record forced a group of human beings to ask, with genuine seriousness and profound care, what is most essential about our civilization? What would we choose to preserve if we could preserve only a small selection? What do we most want to be remembered for? What is the best of what we are? These questions do not require an alien audience to be meaningful. They are among the most important questions any civilization can ask of itself, and the process of asking them is valuable regardless of whether anyone else ever hears the answers. The second answer is that the act of sending the record was an act of profound optimism. The year 1977 was not an obviously optimistic moment in human history. The Cold War was still very much a reality. Nuclear arsenals on both sides were enormous. The environmental movement was just beginning to grapple with the scale of the damage that industrial civilization had done to the planet. Social and political upheaval was still reverberating from the previous decade. Against this backdrop, a small group of people sat down and decided to make an object that would represent humanity at its best and send it toward the stars. They believed that we were worth representing. They believed that the story of human civilization, with all its failures and all its beauty, was a story worth telling. And they believed that the universe was, in principle, a place where that story might find an audience. That belief, that willingness to act on hope despite uncertainty, is itself something worth preserving. The third answer is related to something that Carl Sagan said many times in many different ways throughout his career. A thought that he expressed most memorably in his 1994 book Pale Blue Dot, which was written about the famous photograph of Earth taken by Voyager 1 from a distance of approximately 6 billion kilometers in 1990, at Sagan's request. In that photograph, which was part of a mosaic of the solar system called the Family Portrait, Earth appears as a tiny, barely visible dot, a mote of dust suspended in a sunbeam. Sagan wrote, "Look again at that dot. That's here. That's home. That's us. On it everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives, the aggregate of our joy and suffering, thousands of confident religions, ideologies and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam." The Golden Record is, in a sense, a response to that image. Having seen how small and fragile and precious our world is from the perspective of the outer solar system, having understood that everything human, every achievement and every failure, every love and every tragedy is contained within that tiny point of light, Sagan and his colleagues chose to send some of that precious smallness outward, to say to whatever might be listening, we were here, we were real, we mattered to ourselves, and we hoped we might matter to you too. The fourth answer is perhaps the most scientifically interesting, because it touches on something that the Golden Record represents in the long arc of cosmic time. The record is made of gold-plated copper. It is physically robust. It carries within it, encoded in the microscopic grooves of its surface, actual samples of human sound and human image, the physical traces of human thought and human feeling. In the extremely long run, on timescales of billions of years, almost nothing that human civilization has created will survive. The pyramids of Egypt, which we think of as nearly eternal, will be reduced to rubble by geological processes within tens of millions of years. The continents themselves will have changed shape entirely. The oceans will have been lost to space, or the planet will have been absorbed into an expanding sun long before human civilization would have had time to leave any other permanent trace. But the Golden Record, drifting through interstellar space, far from the geological processes and stellar evolution that will eventually erase everything on Earth, could potentially survive for 1 billion years or more. It is, by a wide margin, the most durable artifact that humanity has ever produced, and the most likely to persist after everything else we have made has vanished. This means something profound. In the most extreme long-term scenario, the Golden Record may be the only evidence that humanity ever existed. Long after Earth has been sterilized by the expansion of the Sun, long after whatever civilization or civilizations succeed us on this planet or in this solar system have themselves risen and fallen, long after every mountain and ocean and city and written word has been erased by the indifference of physics and time, 2 small spacecraft, each carrying a golden disk, will still be drifting through the galaxy, carrying the sound of a mother speaking to her newborn child, the notes of Beethoven's Fifth Symphony, the electric slide guitar of Blind Willie Johnson, and the brainwave recording of a woman falling in love. They will be there, silent and still moving, long after everything else is gone. Whether that is comforting or devastating probably depends on how you hold it. I find it to be both. There is a final dimension to this story that I want to explore, and it is perhaps the one that has stayed with me most persistently in all the time I have spent thinking about the Golden Record. It is the dimension that has to do not with the mathematics of interstellar space, or the physics of record degradation, or the probability of intelligent life, but with the simple human experience of being the species that made this object. We are a young species. Human civilization, by any reasonable measure, is perhaps 10,000 years old, though writing and formal cities only appeared about 5,000 to 6,000 years ago. Modern science is roughly 400 years old. Space travel is barely 70 years old. In the context of the 13.8 billion year age of the universe, we are extraordinarily recent arrivals. We have been building and dreaming and creating and destroying and loving and mourning for a tiny fraction of the time that stars have been burning. And yet, in that tiny fraction of time, we have done something that, as far as we know, no other species on any planet anywhere in the observable universe has ever done. We have built an object specifically designed to outlast our civilization and to communicate who we are to whatever comes after us or alongside us. We have, in the most literal physical sense, written a message to the universe. The fact that the message may never be received does not diminish the act of writing it. This is a truth that applies to human experience far beyond the Golden Record. We write letters to people who may never read them. We build buildings that will eventually collapse. We plant trees whose shade we will never sit under. We do things whose full consequences will not be known in our lifetimes. The willingness to act despite the uncertainty of the outcome, to invest care and thought and feeling into something that may ultimately go unacknowledged, is one of the most distinctively human things about us. It is the impulse behind every cathedral and every symphony and every scientific experiment and every child raised with love. The Golden Record embodies this impulse at its most extreme. It is the letter we wrote to the universe, knowing that the universe might never write back. It carries within it the best of what we have done and the best of what we have felt, sent outward in the hope that the darkness is not as empty as it appears. As of 2026, Voyager 1 is drifting at roughly 17 kilometers per second in the direction of the constellation Camelopardalis, carrying a golden disk covered in the most precious things we could think to send. In November of this year, it will reach one light day from Earth, a milestone that human engineers of the 1970s could only have dreamed of. Its RTGs are failing. Its instruments are being switched off one by one. It will probably go silent within the next few years. And then it will continue outward, silent and eternal, into a darkness we cannot follow. In 40,000 years, it will pass distantly, a red dwarf star that does not know it is being approached. In hundreds of thousands of years, it may drift near other stars. In millions of years, it will be somewhere in the galaxy that we cannot predict. In billions of years, it may still be there, long after our sun has become a red giant and consumed the inner planets, and the Earth is a scorched or vaporized remnant. The Golden Record may never be found. The mathematics say so with quiet, absolute confidence. The physics say so without malice. The statistics say so without apology. The universe is simply that large, and we are simply that small, and the darkness between stars is simply that empty. But the record was made, and it was made with extraordinary care, and extraordinary love, and extraordinary hope. It carries the voice of a 6-year-old boy saying hello in English. It carries the sound of whales singing in the deep ocean. It carries the music that a woman thought about while she was recording her brainwaves and feeling, for the first time, the overwhelming certainty of being in love. It carries a message from a human president to whoever might be listening, expressing the hope that we would survive our time and live into theirs. It carries, hand etched into the metal by someone who was not supposed to add anything extra, but who added it anyway because they believed it needed to be said, the inscription, to the makers of music, all worlds, all times. Whatever the universe answers, or does not answer, we said that. We meant it. We sent it. And somewhere in the dark between the stars, it is still saying it. 1 second at a time, forever. If this story moved you, if it made you feel something about the enormous, beautiful, terrifying scale of the universe we live in, and the extraordinary, fragile, stubborn hopefulness of the species we are, please leave a comment. Tell me what this made you think about. Tell me what you would have added to the record. Tell me whether you think the universe is empty or full. Tell me whether the silence frightens you or fascinates you or both. I want to know. Subscribe to the channel if you want more of this kind of slow, deep, real science storytelling, the kind that does not rush past the hard facts or soften the difficult mathematics, but that also never loses sight of the human beings who are trying, with everything they have, to understand the cosmos and their place in it. The Golden Record may never be found. But it was worth making. It was worth sending. It was worth telling you about. And the questions it raises about distance and time and life and silence and hope are the most important questions our species has ever asked. They are worth sitting with, worth living inside of, worth returning to again and again as long as we are here, and asking them. We are here. We are small. We are reaching. The dark is very large. And we are reaching. Anyway. End.